Braswell with the Nanotech User Facility at the University of Washington, and today we're going to do a training video on E-beam lithography. Lithography in general is a way of transferring a pattern. We use two different kinds of lithography to transfer patterns of very small size: photolithography and E-beam lithography, or EBL for short. Photolithography uses light to expose a photosensitive resist, similar to exposing silver emulsion in the photographic process. Light shines through a photomask like a transparency, and the pattern of the mask is reduced and transferred to the resist. After a short bath in Developer, you can see the pattern in the resist layer. With this method, we can generate patterns many millimeters down to single pattern elements of about 2 micron. The pattern transferred by photolithography will have the same thickness as the resist layer had. That's useful because we can backfill the lines and holes in the pattern with metals or oxides or nitrides to grow a pattern with the chemical and physical properties that we want. Alternately, we can etch the pattern into the silicon wafer itself and create deep troughs and holes where the resist was exposed. In order to create pattern elements with nanoscale dimensions, we need the resolution of an electron beam. In E-beam lithography, we use the electron beam of an SEM to copy our pattern onto a wafer coated with resist. It's a serial process, like tracing a picture out of a book, and so it takes much longer than a parallel process like photolithography. The first step in EBL training is to learn the software. Generate a design CAD file for the pattern that you want, and then a run file for the exposure conditions that you want. So that can be done on your own computer once you've installed the software. The second step is to come in and prepare the substrate. Once the substrate is ready, you can book some SEM time, come in and actually do the writing on the machine. The first step of the EBL process is preparing the substrate. So I start with a clean silicon wafer, and I'm going to rinse it first with acetone to remove any impurities, then isopropanol, and finally a distilled deionized water rinse, and then we'll dry it. So the first step is the acetone rinse. Before the acetone dries, you rinse it with isopropanol. Make sure there's no acetone residue. And then with distilled deionized water. And before the water dries, I use dry nitrogen to blow all the water droplets off of the surface. Both the back and the front. Once this wafer is clean, I can spin coat it with the E-beam sensitive resist and make sure that the bonding to the surface is good. The thickness of the resist layer on the wafer can be controlled by playing with the viscosity of the resist that we're applying and also the speed that it's spinning at. So to apply the resist layer, I'm going to use this spin coating machine here that has a vacuum chuck on top. I just set the clean wafer in the center. And then I'll test to see that the vacuum is holding by starting the machine. If the wafer starts to spin, then the vacuum is good. So I'm going to interrupt that process, and now I'm going to apply the resist. In this case, we're using a 3% polymethyl methacrylate resist. The resulting layer, after spinning this at 4,000 RPM, should be about 300 nanometers. I'm going to apply an excess of the resist. And And the extra volume will all spin off into the bowl. Each pipette full is about 1 milliliter. So for an entire wafer, I'm going to use 4 milliliters. As the thickness of the coating changes, you'll see the color of the wafer also changes. Until we reach our final thickness. And the resulting wafer, 300 nanometers thick, should be green color. Full spin time is 45 seconds. Now I'm going to transfer that wafer to a hot plate at 180 degrees for 1 minute. That'll drive off the excess solvent and solidify the resist. After 1 minute, I'm going to pull the wafer from the hot plate. Let it cool. And then before we pattern the surface, we'll break this into smaller pieces. The chamber size on our system is limited to about 5 centimeters in the X and the Y direction. So we can't write on this entire wafer. So the next thing I'm going to do is break it into smaller pieces so that it fits into our system. This wafer is single crystal silicon, and it'll break. It's so pure it'll break along a perfect cleavage line in the crystal plane. If I can just get a fracture started, it'll propagate all the way through. So I can cut a perfectly square piece from this. The ideal size for our chamber is about 1 centimeter squared. The surface of this resist is featureless, so in order to have something to focus on so that I know that the resist is at the right height, I'm going to carve numbers into the corners on this chip. They don't need to be deep enough that they score the silicon, they just need to be through the resist layer. So I'm numbering the corners clockwise, 1 through 4. That'll give me a reference point when the chip is in the system. In addition to loading the chip, I need 2 standard samples. First, I'll load gold nanoparticle substrate because it has very good contrast and we can use it to optimize the beam before writing. It's kind of like sharpening your pencil before you draw a picture. And the second sample that we need is called the Faraday cup, and it's basically a 75 micron aperture that collects the entire beam so that we can measure the amount of current that's coming through. From that current, we can calculate the dosage that we need to expose the resist fully. And one last step before I load this into the chamber, I want to blow the debris from the surface of the chip that might have landed there from scribing the numbers into the corners.